So the next topic in identities is the sum and difference identities, and these are also known as compound identities. So we won't be looking at the proofs for these. However, I did post videos in the Google Classroom if you want to see a visual proof of how when we add these two angles, we end up with these formulas. So in pre-calculus, you only have to know how to use them in order to simplify and or manipulate certain angles that are not on the unit circle, okay? So the whole point of these is to either expand or condense, all right? So you can go either way with these formulas. Now, you do not need to use these if the angles that you see are standard on the unit circle. The point of these is to rewrite a trig expression so that we can use angles that are standard on the unit circle so we can get an exact answer. So the first thing I want to look at is the sum identities. There is a sum identity for sine. There is also a sum identity for cosine. So x and y represent two angles, and we are adding these two angles. Now I need to make clear that these are two different angles, right? If they were the same, then that would be a completely different type of identity, which we will look at in the next video, okay? So based on the proofs, you can look at these in Google Classroom if you want. If we have sine and we are taking the sum of two different angles, then we can rewrite this as sine x times cosine y plus cosine x times sine y. So for sine, notice that they are paired. The trig expressions are not paired with themselves, all right? So we have sine times cosine and cosine times sine. And then the difference between these two terms is that the angles will change. So in the first term, sine of x, and then in the second term, it's sine of y. And then also, notice that when we are taking the sum of these two angles, and the expansion, we are also taking the sum of those two terms. So sine means you have the same sign. So sine, same sign. Now, if we look at the double, or not the double, the sum identity for cosine, we are taking the sum of two angles. And if you notice in the expanded portion, it is paired with itself. All right, so cosine is paired with cosine, and then sine is paired with sine. Now for cosine, you will change the sign, all right? So change sign. And I'm talking about for the sum identity for cosine, you will be taking the difference in the expanded part, all right? And I'm saying it like this because there's S for same and then C for change, okay? And then we see the same patterns with the two difference identities for sine. For the difference identity for sine, they will not be paired with themselves. So we have sine times cosine minus cosine times sine, all right? And then the angles will switch. And then for cosine, it'll be the same thing. Each trig expression will be paired with itself, but again, the sign in between the two terms will change. So if you're confused on which one to start with, if you look at the, I guess both identities, we see that we start with sine of x, so we start with sine of x. Start with cosine of x, start with cosine of x. So as long as you recognize that, then that means, oh, for sine, it's going to be paired with cosine, which means the angle for that cosine will be y. Or if I'm looking at the cosine double angle identity, I need to stop saying that. This is the sum identity for cosine. Then it's going to be cosine x and it's paired with itself. So every single identity, it tells you what will be the first term, whether it's going from the condensed to the expanded or the expanded to the condensed, okay? So how do we use this? The instructions say use the sum and difference identities to find exact values of each of the following. So I see cosine of 15 degrees. 15 degrees is not a standard angle on the unit circle, right? Therefore, we can't evaluate this and get an exact answer. So I want to use two angles that will basically create 15. So what two numbers, whether I take the sum or the difference, create 15? Well, 15 is smaller than the smallest standard angle that we have on the unit circle. The smallest one besides 0 is pi over 6 or 30 degrees, all right? So I'm going to have to use some subtraction. So let's do cosine of 45 degrees minus 30 degrees, okay? Now, if this was cosine of 30 degrees, we wouldn't need to expand it. You would just simply evaluate. The whole point of these identities is to get it in the form where you can evaluate and use the standard angles on the unit circle. Okay, so I'm using cosine, which means I'm going to have to go to the expanded version to evaluate this. I can't just type in, oh, this is cosine of 45 minus 30, or cosine of 30. This is not distribution. We are looking at one single term here, okay? So make sure you're not thinking just because it looks like we can distribute, that's not what's happening. This is a transcendental function, and we have an input of 40 minus 30. So we have to use a formula in order to actually evaluate this, and it's going to be the difference identity for cosine. So for cosine, it's paired with itself. So I have cosine times cosine, and then because I have a subtraction, it's going to be a plus, and then I have sine times sine. Now the input, this one's pretty straightforward. 45, 30, 45, 30. And then don't forget your little degree symbols. So now the whole point of this was to expand it and rewrite it using a difference of angles so that we can evaluate using standard angles on the unit circle. Let me get some space. So cosine, all of these are in first quadrant. You pick most of them, so try to stick to the first quadrant. You shouldn't be using like 150 minus 135. I mean, you can, but you're creating more work for yourself and you're having to like reflect and travel to other quadrants. So cosine of 45 is going to be root 2 over 2, family of 4s. So we're going to rewrite this as root 2 over 2. Cosine 45 is equal to root 2 over 2. Cosine of 30, that's going to give me root 3 over 2. And then sine of 45, that's also root 2 over 2. And then sine of 30 will be 1/2. So with these identities, you're going to see the coordinate pairs. Okay, so it'll help with that. All right, root 3 times root 2, that's going to give you root 6. And then we'll have 2 times 2, which is 4. Plus root 2 times 1 is root 2. And then 2 times 2 is 4. And then you'll want to just reduce these to one term, because you may run into multiple choice and you need to know how to combine radicals. You can only truly combine them when you're multiplying, okay? When you're adding two radicals, like radical 6 plus radical 2, you're not going to get radical 8, all right? They are two bases, therefore two separate two different bases. This is base 6, that's base 2. We cannot add those two together, okay? All right, next we are working in reverse. So now I have the expanded version. I see sine of 75, cosine of 15, cosine of 75, sine of 15. These are not on our unit circle, all right? So let's try something else. Let's try condensing it using, it looks like we're doing sine because I see that sine and cosine are paired, and we have subtraction. So it will be the difference identity for sine. So I'm going to do sine of 75 degrees minus 15 degrees. Now, when I do this and I apply the difference, I'm going to end up with 60 degrees. 60 is on the unit circle. It's going to be in quadrant 1, and that will be root 3 over 2. All right, so here's a multiple choice. Which of the following is equivalent to the expression cosine pi over 8 times cosine pi over 16 minus sine pi over 8 times pi over 16? So I see that cosine is paired with itself. Therefore, this is going to be a cosine identity. And I see that minus. And for cosine, it's going to change signs. So we have the sum identity for cosine. So I'm going to do cosine of pi over 8 plus pi over 16. Now to combine these, we need a common denominator. So I'm going to multiply pi over 8 with 2 over 2 to get that 16 in the denominator. All right, with the common denominator, I end up with 2 pi plus pi, so that'll be 3 pi over 16. So the correct answer for this one is C. All right, example 8, given cosine alpha is equal to negative 1/3 from pi over 2 to pi, and cosine beta is equal to 2/5 from 3 pi over 2 to 2 pi, find the following. Okay, so this is telling us that for the angle alpha, the cosine of this angle will be negative 1/3, okay? So go back to geometry. You need to think SOHCAHTOA. this is telling you how to set this up. All right, if I think SOHCAHTOA and I'm looking at cosine, I have adjacent over the hypotenuse. Now this is negative, right? And cosine is negative in 2 quadrants, right? That is the domain restriction. Pi over 2 to pi is telling you, oh, even though cosine is negative in 2 quadrants, we can specify which quadrant it's going to be here, okay? Because we have 0, pi over 2 is up here, pi, and then 3 pi over 2. And if it's saying from pi over 2 to pi, we are going to be in the second quadrant. So over here to the side, what I want to do is I'm going to draw a sketch. And SOHCAHTOA, that's for right triangles. So I'm going to draw a right triangle in quadrant 2. And this is for angle alpha. Now my adjacent side is 1, and then my hypotenuse is 3. So it is negative, and I understand that we are looking at a triangle, and that's the length of a side, but I'm going to put a negative here so I remember, okay, when I evaluate in this triangle, my adjacent side is going to be negative. Now I can already see that there is a sine alpha, so we're going to have to use the opposite side anyway. When you're constructing these triangles, it doesn't hurt to just solve for the one side that's missing, okay? So for alpha, we can use Pythagorean theorem, which is a squared plus b squared is equal to c squared. So I have negative 1 squared plus b squared is equal to 3 squared. I get 1 plus b squared is equal to 9, and we get b squared is equal to 8. So we have b is equal to the square root of 8. This can also be rewritten as root 2 times 2 times 2. So we get 2 root 2. You don't have to simplify it to that. Again, sometimes you might see this as a multiple choice, so it helps to practice that algebraic manipulation. And we aren't using plus or minus because it's a side length. If this triangle was just in space and not on a coordinate plane, like if I just drew it here, all the side lengths would be positive. But on our coordinate plane, because we're traveling to the left, the x's are negative, and then because we're going up, the y's will be positive. So that's the first triangle, and it looks like we have a second triangle. So this says cosine beta is equal to 2 fifths. So again, SOHCAHTOA, I have adjacent over hypotenuse, and this time it's positive, okay? Which means it's going to have to be in either quadrant 1 or quadrant 4. And my restriction says 3 pi over 2 to 2 pi, so that means we'll be in quadrant 4. So I'm going to draw my right triangle in quadrant 4. And this is for angle beta. So the ratio is 2 over 5. So for cosine, that will be my adjacent hypotenuse. All right, so I might as well find the opposite side for this one as well. Again, we'll use the Pythagorean theorem. So I have 2 squared plus b squared is equal to 5 squared. 4 plus b squared is equal to 25. B squared is equal to 21. So we have b is equal to the square root of 21. So that opposite side from our angle will be root 21. All right, so now that we have all the pieces, we can go ahead and start solving these different parts. Part A says solve for sine alpha. All right, well, sine alpha is going to be the triangle in quadrant 2. I can tell by the angle, okay? Sine is going to be opposite over hypotenuse as it pertains to angle alpha. And the opposite side is going to be 2 root 2, and the hypotenuse is 3. So we'll get 2 root 2 divided by 3. Part B is asking for sine beta. Again, we're going to look at opposite over hypotenuse. But now we're going to be using the triangle in quadrant 4, right? Because it's specifying angle beta. So what I should have done before, well, not should have, you don't have to, but hopefully you just remember. Because we're in quadrant 4, sine is negative because we're going down because y is negative, okay? So I'm going to notate that just so I don't forget to use it. So for part B, it'll be opposite over hypotenuse. So negative root 21 divided by, that's the adjacent, divided by 5. So sine beta is negative root 21 divided by 5. Now for C, cosine of alpha plus beta. Common misconception is that people will try, oh, let's do cosine alpha plus cosine beta. Oh, cool, they already gave that to us. It's that misunderstanding that alpha and beta are inputs for cosine. They are not their own entities. They are angles, but to truly evaluate cosine, we need those angles in their own trig expressions, right? We can't just add those two together, okay? Also, we don't know what the angles are. Sometimes people will be like, oh, cosine alpha is -1/3, so they'll do cosine -1/3. This is very, very wrong. And you should recognize this because coordinate points are inputs for inverse trig, not regular trig expressions, which this is, okay? Inputs for regular trig expressions are angles, okay? So there could be a lot of mistakes that occur, but as long as you remember your identities, you can at least steer yourself in the correct direction. So like I said before, this is a compound identity, sum identity for cosine. I know that my first term is going to be cosine alpha. I can see it, all right? The condensed and the expanded identities will tell you where you need to go. So I found my cosine alpha, and then I'm also thinking, okay, for cosine, it's paired with itself. So that means I have another cosine. I already used cosine alpha, so I'm going to use beta. And then for cosine, the sign is going to change. I see a plus, a sum of angles. So in my expanded version, I'm going to use minus. And then since cosine is paired with itself, that means sine will be paired with itself in the second term. All right, so cosine alpha was given to us in the instructions. It is -1/3. Cosine beta was also given to us. That was 2/5. Sine alpha we found in part A. That is 2√2/5. I'm sorry, 3. And then sine beta was found in part B. That's -√21/5. From here, it's just some algebraic manipulation. -1 times 2 is -2. 3 times 5 is 15. And then in the numerator, we technically have 2 times square root of 2 times negative square root of 21. Now, we can multiply the two radicals because it's technically 2 to the power of 1/2 times 21 to the power of 1/2. So we can multiply those two bases together. The 2 on the outside, that's just to the power of 1, okay? So that's going to have to stay, these are not like terms. It'll have to stay with itself. So we'll end up with the square root of 42 divided by 15. With the sum and difference identities, going from the expanded to evaluating, you should always end up with a common denominator. If you did not, that means you did something incorrect, okay? And it's because we're using coordinate points from the same, we're using sides from the same triangles, okay? So the hypotenuses should cancel out. All right, so we can go ahead and condense this a little bit. We should end up with, for the numerator, we'll have -2 minus 2√42/15. If you really wanted to get into simplification, we could factor out a -2. So we have 1 plus √42/15. It's not necessary, but getting that -2, that common term to the front, kind of helps clean up those two terms. And then even further, you could do -2/15 times 1 plus √42. But again, if you're doing this on an assessment at Plano East, you can just stop right here. We do want to see that one term. All right, the last part of this, it says simplify the following. That should just say rewrite. We're not simplifying, we're just rewriting using a double angle, a sum or difference identity. So this is cosine, so the cosine x will be the first term. It's paired with itself, so it'll be cosine y. And then we change the sign for cosine, so I end up with sine x, sine y. And then part B, it is partially evaluating. We cannot evaluate the x because we don't know what that angle is. We just know it's an angle, okay? So we're going to rewrite it and then do some evaluation to solve for part of it. So I see that it's sine, so my first term will be sine x. And for sine, it is not paired with itself, so I have cosine of pi over 6. For sine, this sign will stay the same, so it will be subtraction. But now my angles have to switch with which trig expression. I don't want to rewrite sine x again, okay, because I already have sine x over here. So it's going to be cosine x of sine pi over 6. Now from here I can evaluate cosine pi over 6, but the sine x will stay the same. So cosine pi over 6, that is going to be in quadrant 1. That will be root 3 over 2, and then times sine x. And then sine pi over 6 is going to be 1/2, so I have 1/2 cosine x. And since we can't do anything else with the x's, that is your final answer. All right, the last video will be on double angle identities. I kept saying it, so if you need help with that one, just watch that video once it's posted. All right, hope this helps.